Good morning and welcome to this episode 411 of Kodsnack. This episode is a bit of a follow-up to episode 389 where Robert Wikandertalked talked in Swedish about verification of circuit designs. And afterward, Robert mentioned that we really should ask Wilson Snyder to come on the show and talk about Verilator. So here we are. Wilson works with CPU and other hardware design and is one of the lead developers of Verilator. When you design hardware description languages come in really handy. You simply use them. Well, not simply. You use them to describe hardware precisely. And then you can generate runnable code simulating that hardware from the language and then run your batteries of tests against your simulated hardware without needing to actually manufacture it physically. Very nice. And Verilator is one of the major tools for turning code written in the Verilog hardware description language into C++ or System C. The major competing tools are more on the interpreter side, while Verilator is a compiler. And that means that Verilator usually has a pretty great performance advantage. And it's also GPL licensed. And as always, if you enjoy the podcast, please tell someone else about it. Leave a review, tweet, phone, or just plain talk to people. And you can also support us on Coffee or buy shirts in our shop. The links to all that and everything we talk about are as usual in the show notes. Now, let's talk to Wilson Snyder. Welcome to the impossible to pronounce Swedish podcast Kodsnack, Wilson Snyder.
Thank you.
So we had an episode a while back with Robert Wikander, who talked about hardware verification and various related things. And one person he mentioned was you in relation to this. So you want to give a brief introduction to yourself?
Yeah, sure. As you said, my name's Wilson Snyder. So I started work at sort of my first permanent job after college was at Digital Equipment. And there I was doing a bunch of sort of RTL design, so chip design, and eventually moved into architecture. But I also started working on a tool that was called Verilator. It was sort of an open source tool that could do simulation. And I had a bunch of other sort of tools that I was working on. And then through basically a happenstance, so to speak, that got put into open source when Digital merged with Intel. And then I had a bunch of other jobs and kind of lost track of it, and other people were working on it. And then finally I got back to a startup again doing chip design and picked up the tool that was now open source and developed it some. And then I moved to another startup and developed it some more, and another startup and developed it some more. And so it just kind of started as a hobby and now sort of has a life of its own with other people working on it and sponsorship and all sort of those great things. So sort of the normal sort of work as hobbyist project sort of gets its own life outside of normal work.
Yeah, clearly. So it started off as closed source at Digital.
Yeah, so it started off as closed source because basically at that time synthesis was just new, which synthesis is like the converting of, basically the programming language used to design chips into actual hardware gates. And we wanted to be able to use that new tool to, make a design, and we didn't really have any way of kind of matching the languages. So I was like, okay, well, let's just translate it into C++, which we could then compile. Actually, I think at that time it was C, which we could then compile. And it was, basically used only by one group, and then it got picked up by another group in Digital. And then after I left, when they joined, basically our group got split out to Intel. So the tool sort of had to be used by two different companies, and they were like, how are we going to manage this? This is a real pain in the butt. I was like, I know, let's just, open source it, then we don't need to deal with it. And, that and another tool escaped.
Yeah. So what time period was this roughly?
Oh yeah. So this was a good time ago. This was, I think the first code in Verilator was like 1990, maybe 1993. So it's quite a long time ago in the software universe of things.
Yeah.
Way back, I think at that time, GNU Emacs was of course open source, and like we actually, when I was at Digital, we had a presentation by someone we had given a computer to, to just see if they could port their OS, named Linus, and so it was like back before it was like anything real.
Yeah,
entertaining.
Clever guy. He might turn into something one day.
Yeah, it was a good donation as it turned out.
Yeah. Worth the investment. So was it released as GPL then, I guess?
Yeah, so we got it under GPL2 and then later it upgraded to GPL3. Yeah, and it's kind of a good escape story. Although now there's really there's probably at least one line of code, but I doubt there's more than a few dozen lines of code that predate back to that original heritage.
Yeah, it's fun to go back and dig up, see what the oldest thing you can find is.
Yeah. Well, all the history's in Git. I should do that. Could be interesting.
Yeah.
I might get scared of something that needed refactoring from way back when. It's like, oh my God, who wrote that?
It was
and
me
you realize
again.
It's yourself. But yeah, it was me again. Younger me. It was a little more naive. That's okay. If I got the job done for over 20 years, it's probably good enough code.
Oh yeah. It had a good return on investment there.
Yeah.
So were there other tools like this at the time, or was this sort of like the first one to do this particular thing?
Yeah, so what it's basically a compiler.
Mm-hmm.
So at the time, most of the other tools were basically interpreters. I mean, they were higher speed interpreters, but they were still interpreters. Shortly after Verilator, there was a commercial tool that came out. It was sort of the first compile-ish tool, but it's still more interpreted. So Verilator is still kind of unique, and even though there's sort of 3 major commercial players, maybe 3.5. Verilator is actually faster than most of them in most cases. So a lot of companies, even though it supports sort of a subset of the language, it supports, the most common stuff. So a lot of commercial companies use it for chip design, including like Tesla for their self-driving chip cars, self-driving chip for cars. So they use it because basically it runs a lot faster, and the more cycles you can run through, the bigger confidence you have. And it's also really good for software development because you don't need a license and sort of all the normal reasons that drive to people liking open source and people making enhancements, and it's sort of it feels a good niche. So it's not exact overlap with commercial tools. I think it wouldn't be anywhere near as successful as it's just a true overlap.
No, of course that makes sense. So I guess roughly speaking, the commercial alternatives trade off like lower performance for implementation of more things then?
Yeah, exactly. Right. So the commercial tools, they support a bunch of features and, timing constructs, a bunch of things that are, important. And if you're to be able to do everything, you have to be able to do them. So like you're designing a chip, you generally want to do X simulation. There's a bunch of things, or analog simulation. There's a bunch of things you need to be able to do to prove the chip. So you'd have to be able to have that tool for other reasons at least. But that doesn't mean that, 100% of your simulations would have to be using it. Using something like Verilator means you can, move the 90% of the easy stuff to something else that runs faster, and then the other 10%. At least that's my story. And
yes. So is it sort of is it a very important design decision to not support these sort of last 10%? Or
yeah, I mean, the good thing about being open source is it's the worst. Someone complains, the worst case they can just not use it and I don't lose any money. So there is actually we're doing a bunch of work. So there's the Chips Alliance, which is a forum that just started underneath the Linux Foundation that is sponsoring open source tools for chips design, and it's maybe now 2 years old or so. So this is a new thing, by the way. Even though Verilator has been open source hardware design for now, I guess, over 20 years, we just decided, there probably has only been a real interest in sort of serious design tools, as opposed to sort of PhD sort of projects just used by universities for maybe 5 years or so. So anyways, the Chips Alliance is sponsoring some work to add a bunch more new features to Verilator, because their goal is to be able to get it to be able to do not 100%, but maybe 98%, enough that someone can, basically tape out a chip using only Verilator, because their goal is to be able to run all the tools necessary to actually make silicon design and actually even tape out a chip using just open source tools.
Well, yeah.
So we'll get there over a few years.
Yes. So are there any sort of major obstacles to implementing these features?
Well, the major obstacle is getting the people to work on it.
Oh yeah, of course.
So there is sponsorship. So there's some people working on it full time.
Yeah.
I think that's probably the main barrier. There's of course a bunch of technical decisions that in retrospect maybe should have been done differently. But if we'd done it complicated in the beginning, maybe it never would have happened. So I can't lose much sleep about that.
No.
So there's certainly some challenges, but there's nothing really fundamental. There's the one good thing is it's well understood how to do these problems. It's not like it's a new problem, so to speak.
No.
Because people have been doing simulators for 20 years.
Yeah.
But we also have a bunch of work to make it yet faster. So that's kind of the more interesting researchy topic.
Yeah.
So if people are interested in compilers and how to make things run faster and how to optimize compiled right down to the hardware, we certainly would love help if there's people that listen to this.
Yeah, I mean, this feels like one of those places where it's even clearer than usual how higher performance can actually be a big benefit in itself, because it allows you to do more tests quicker, get more confidence, and so on. I mean, people like to talk about you shouldn't be optimizing too much too early, but this feels like a case where there are clear benefits and clear goal with the optimizations.
That's right, and not only that, I mean, chip design is the place where basically you use your own product, right? So we generate the next CPU, and then 2 years after that, we're using the CPU because we want the performance to generate the next CPU. So it has its own feedback cycle in a good way.
Yeah.
Actually, like the chip industry as a whole, which is why you get the exponential growth in performance.
It's a fascinating area. So you were away from the project for a while there, and then you came back, or it came back to you?
It sort of came back to me, I guess I would say. So it got released by someone called Dwayne Galby. He's the one that sort of drove it through getting it open source, because I was gone from Digital/Intel at the time. And to have a sort of a home for it to land, we made a website which basically had the tarballs, and there was some development that sort of continued on in Intel, and he was one of the people working on it. And then I didn't really have any need for it at the company I was at the time. And it wasn't until about 5 years later that I moved to a startup, and we wanted to use a new language called System C, which is basically a C++. It's a language based on top of C++ for architectural design. And I wanted a way of hooking it in, and Verilator is sort of the perfect thing, since it compiles to C++, which would naturally, since it has the same underpinning language, worked really well. And that was before there was any commercial tools that did that. Maybe about 5 years later, there were some commercial tools that did something similar. So it just kind of filled a niche that I needed, and so that's where version 2 came from, is it was a rewrite to be able to use System C integrated with it.
Yeah, that's kind of fascinating as well, that there weren't any commercial tools. It doesn't feel like people speak all that often about circumstances where open source is actually ahead of commercial tools. It feels like the usual stories that someone talks about some commercial option and someone wants a freer version or a more open version, and then they create that, and then it sort of catches up. But in this case, open source is actually ahead of commercial alternatives.
Yeah, I think it depends on what the market is. I mean, if it's something mature, like, I don't know, an image viewer or something, obviously, then there's a lot of commercial alternatives. So open source kind of models on, let's make a nice new version of this with a bunch of bugs fixed and new features, right? But I think if you look in the more researchy space and sort of the leading edge, you'll find that a lot of companies have their own tools because there are no commercial offerings. So going way back to the the 90s, a lot of the design houses had their own versions of schematic editors or what have you, all these different EDA tools, and they developed them in house. And it wasn't until Cadence kind of has been around a long time, but Synopsys, which is a company that started by providing these synthesis tools, and then later got into a bunch of other things. It wasn't until the maybe mid-ish to late 90s that most of the companies doing chip design sort of settled on the same couple companies and had very little internal development. And I think universities are somewhat similar, right? You have a ton of universities doing researchy projects, and nowadays, fortunately, they tend to open source it a little more formally, where before maybe it was just lost in some papers printed out in a thesis somewhere. Some of that stuff catches on, a lot of it doesn't, but to some extent it is open source. And then you have someone that then, maybe even the same master's or PhD candidate, they're like, especially if they're from Stanford, they sort of decide, I'm going to make a company to now make this into a real tool. Then they make it into a real tool. Then it becomes popular. Then now that it's popular, someone makes an open source. But actually, it originally started open source because it was research. So it's a spiral feedback, which is good. I mean, that's the good thing, right? Is when you have sort of these innovation feedback cycles and things sort of morph between open source or Git's a good example, right? Git started open source. And now you have GitHub, and this is back and forth flow, which is great.
Yeah. And it's nice that there's this push to make the whole chain, so to speak, open source now as well.
Yes.
I mean, that's something that Robert mentioned as well, that he was really excited about.
Yeah, and the other interesting new push, which the CHIPS Alliance is working on, is this whole push towards actually having open source hardware. So,
yes.
Yeah, there's a bunch of designs, like RISC-V is sort of open source architecture, and then there's implementations of RISC-V, which are open source CPUs, and there's been some open source, like OpenCores as an example, for a long time, maybe 20 years or more. Like I used a couple of those in my startups, but there hasn't really been sort of, I guess I would call it sort of serious industry developed hardware open source in the same way that there's Linux or serious tools that are developed by a lot of companies. And that's one of the things the CHIPS Alliance would like to see and is helping to develop, is the idea that, well, if you have 3 or 4 companies and they all sort of have the same need, figure out a way if you can make that open source, as opposed to having to go to a third party that you have a closed source license, which doesn't mean you could easily have a commercial organization that's sponsoring the open hardware, and that's totally reasonable, right? And that way you get your support. But the idea that what is produced as an end product is open source, you can see it, you have sort of the community around bug tracking and making improvements and contributions back. And generally, there's also the assumption, although it's not a requirement, that there's no royalty associated with it because the code is actually open source. So this is a new thing. There's been a couple of, like I call them demo chips, a little bit more that's been produced, but it's not really a mature idea yet in the sort of professional, in the really large design houses. Like I don't know, but I've never worked for Intel, so I don't know. So it's complete speculation, but I would speculate there probably is no open hardware design hardware on a Intel CPU, for example. No. But I would also speculate that probably in 10 years that'll be different. I bet there will be some that's on the chip.
So there's a lot of interest around this, I take it.
Yeah, there's a lot of interest around it because in the same way that open source solves a lot of problems with software design in terms of reuse and availability and not having to pay a license, for every little library. I mean, imagine if you had to pay a license for libgcc, right?
Oh, yes.
It'd be very frustrating. You used to have to. You used to have compilers that were owned, back at digital, there was a digital compiler and you had to buy the digital compiler. Yeah. So it wasn't that long ago, but that's where we are now in chip design. You have to pay for each of these little components you instantiate. And instead, if it was a fixed fee, you pay the fixed fee for whatever support you need to get it working. And then you don't need to pay every time you use it. I mean, that would be a great accelerant.
Yeah. So things could start moving even more rapidly in the coming years.
Yeah, things move more rapidly, exactly.
Oh,
and as chips get bigger, the problem gets bigger. Just like as software gets bigger, it's more important to have good libraries. The same is true with chip design.
Yeah. So what do you think, as non-hardware developers, what do you think will be the first result we see from this movement? Will there suddenly be new chips, new exciting chips in the platforms we program for? Or
I think there'll definitely be some new chips. We're seeing a little bit in, again, RISC-V is an example where you're those are the newest companies, so those are the ones that seem to be adapting it sooner. So certainly those people doing FPGA design, which is sort of halfway between hardware and software, because it doesn't require making your own silicon, of course. Yeah. There's a lot of benefits now. You can download a core, and there's also some open source ARM cores and open source MIPS cores, and you can download those now and build something and prototype it. And there's actually some companies now that are, if you even wanted to fab your own chip, you can do it for like $50K, which is, in the context of silicon design, $50K is like nothing. Not for university. But in terms of the ultimate end user, you're going to see a bunch of new chips. Like you look at the Raspberry Pi just had their new little chip that they self-spun, and that particular chip was actually, it isn't really open hardware as far as I know, but you can imagine that there'll be a proliferation of similar small designs that once you don't have to worry about the logistics of putting together all these pieces, it'll be much easier to put them together.
Oh yeah, so we might see more and more, say, custom hardware, so to speak. More companies building their own hardware components, more or less.
Yeah, I think we will. Although there is the competing problem, which is making a chip is getting more and more expensive just because they tend to get bigger and mass costs are really expensive. So there's an interesting, sort of counter force too. So we'll have to see how they recognize.
There we go. I just had a little hardware crashed there for a second. I'm back now. Yeah, okay. So there's sort of a competing force there. Is there anything that can be done about that? Will some other movement work to bring down costs on the complexity side when it comes to manufacturing?
Oh, that's an interesting question. The fundamental problem, I think, is sort of the physics to manufacture the chip is just insanely expensive. I'm not sure there's going to be a great solution to that. I mean, long ago there was standard cells, which helped a little bit there. I'm not sure that's going to come back though. So it's an interesting question. I think probably something that looks like FPGAs will continue to be pretty standard. You can imagine that a lot of FPGAs, actually probably all of them now, they also have relatively standard blocks that are sort of hardened and put on the FPGA processors, for example, or DSP units or something like that. So we'll probably see a lot more of that. And at some point, if the silicon is so cheap, it's almost like, well, you can throw that stuff in there and the cost is so small. It's, nowadays a microcontroller is, invisible from space, so to speak. It's just, you can fit millions of them per millimeter. It's almost free. So you can imagine that there'll be a lot more integrated blocks and things like FPGAs, and only certain people will use them, or you'll have better synthesis to be able to use them. Well, it's an interesting environment. You have sort of the usual finances causing new techniques to be developed, and then those new techniques to be developed might even change some of the finances of how you build chips.
Yeah, it's going to be exciting. I'm thinking as a regular soft writer of software, so to speak, and a user of Macs to do my development. I start thinking about Apple switching to making their own chips and having more and more of their own custom silicon in their machines. Would it be crazy to think that more companies will make more of their own chips?
I certainly think more companies will. I think one of the reasons that Apple has been successful in making their own chip is basically they were able to license a while ago the ARM architecture. So x86 is still not and was never an open architecture, even though there was, of course, AMD and Intel and some other random people longer ago. They basically, other than AMD, they basically reversed, all those smaller companies, they reverse engineered x86. And there is sort of you can't just say, I want an x86 license and build it and be able to say your chip is x86 compatible. It's not a thing. But ARM, you could do that. So they were able to leverage all of the infrastructure that had been built around the ARM architecture. But ARM still has license fees, of course. For better and worse, I think there's definitely some benefits of having control over the architecture from one place. Don't get me wrong.
Okay.
But that is definitely something that has enabled companies like ARM and my current employer, Marvell, and others to basically do their own CPU design and be able to sort of pick their own niche of what they want their CPUs to look like, which 10 years ago, even though there were other CPUs on the market, the reality is basically everyone was buying either Intel or AMD. And, if they didn't have the chip you want, for the most part, if you were building a general purpose computer, you kind of were out of luck. I mean, there was embedded, there was always many choices. But in terms of general computes. So I think we're going to see a ton more companies that basically decide to build their own hardware to pick their particular niche. And the key thing is from a software developer standpoint, whether it be ARM or RISC-V or even x86, you guys should be able to rely on, no matter what the hardware is at the top, unless you're writing device drivers, you should be able to ignore what the particular architecture is. And that's the way it should be, right? It should be a lower layer that if you're working at the higher layers, you just don't have to worry about.
Yeah, I mean, in one way, yes, definitely. But in the other way, I'm kind of excited about more unique hardware in different places, which can be used for a great benefit. Because I think back to like the Amiga, which had its own custom chips that made it able to do like so much more than a 386 PC for 10 times the price. I want to get back to those days where people can dig in and it's like, but this machine has this chip and I can use it to make these things. Then they're 10 times faster than your Intel PC over there. Yeah.
Well, I had an Amiga, so I understand that viewpoint. Well, I think you're seeing that with ML. Machine learning is a case where there's a ton of different architectures, and there really is yet no standard, for better and worse.
Yeah.
And you can get great speed ups if you're using that. GPUs, of course, being the example from 20 years ago. Now there's relatively standard pipelines you can run on top of it. I think an example where you're probably going to see more of that coming up is DPUs. So DPUs are basically the data processing unit accelerator chips. So it's good. Think of it as a network interface chip on super steroids, plus probably something doing NVMe, doing disk acceleration, like encryption, things like that. Yeah. Sort of data offload unit. And I suspect that what we're going to see is, in the same way you have a GPU that handles offloading all the graphics, you'll have a DPU that handles offloading sort of all the networky stuff, which a lot of that right now is done in the hypervisor. So if you go to like a big cloud provider, they tend to have something that looks just like a DPU and probably is a DPU sitting outside of their CPU complex. And that's what actually does the virtualization of things like networking. So when you're running on a cloud provider and you're talking to what you think is a disk, it's probably not really a disk. It's probably talking to another chip, which is the DPU, and then that has a network connection to the real disk. Well, to a box, to another box, box, whatever. However deep it is depends how much money you're paying for your storage. You get the idea. But that has a lot of benefits, right? Because now the hypervisor doesn't have to be involved in moving every single packet or disk block or what have you. And also it lets the cloud provider basically do migration of your data. So if the machine goes down, they can just migrate it to another physical machine. And as far as you're concerned, you always have your IP address, and nothing bad has happened other than maybe a small hiccup in the actual time they had to physically move the machine.
Yeah. I have this feeling that it pays to think about the hardware and the chips to a whole different level than most of us do regularly.
Yeah. Well, it literally pays me, so
yeah, exactly. We pay you to do this thinking. So yeah, should we talk a bit more about Verilator? Perhaps we mentioned it in the beginning, but not much more than that. So to start, what does it do? How does it work?
Yeah, so basically the idea is it takes, the input is a language called System Verilog or Verilog, which is a hardware design language. So it's like a lot of other languages, except for you basically need to think in complete parallel. So for example, you have flip-flops and gates, and obviously in a real chip, those all operate in parallel. So when you're writing the code, you need to realize that there's all these, thousands, millions of blocks that are all operating in parallel, as opposed to sort of your normal computer language, right, where everything's sequential. But System Verilog does have sequential blocks too, so you sort of need to know which blocks are parallel, which blocks are sequential. So you write up all this stuff in System Verilog, and then what Verilator does is it does all of the normal compiler-ish stuff, which is parsing and lexical analysis and warning about bad language constructs and unused variables and all sort of the normal languagey things. And then what it does is it actually builds a representation of those things that can happen in parallel, and it performs a bunch of optimizations that look like a synthesis tool. In other words, if you have a bunch of parallel constructs and nothing's used, in other words, let's say I make a bunch of gates and those gates don't go anywhere, they can't propagate to any sort of output, then it can rip them away because it knows there's no way to observe them. It's sort of like the idea of unused code, but it's unused code in a parallel sense. So it can do optimizations like that. It can flatten things. So like if you have an inverter that then feeds to a bunch of other statements, it can push that inverter in so it no longer needs to run code on that inverter. It can do a bunch of electrical like optimizations, like Boolean optimizations and things like that. And then finally what it does is once it has this simplified, call it a net list, it then needs to schedule it. So it needs to figure out how to represent this parallel construct in a CPU core, and actually supports multi-threading, so multiple CPU cores. So then it makes these super complicated graphs that represent all these dependencies between the things, and it needs to go through and do all these graph optimizations to figure out how to convert this into these long sequences of straight line code that are going to operate on the CPUs. And then finally, what it spits out is regular C++ code that represents these couple of straight line paths, one for each CPU, sort of a little more complicated than that. But for sake of this talk, straight line code for each of the CPUs that it's going to run it on. And then you run it through your normal C++ compiler. So it doesn't spit out assembler, it just spits out C++ code, and it relies on leveraging all the normal GCC optimizations, which is a great thing because then you can run it on whatever C compiler you want, and you can take advantage of as they improve the technology of the other C++ compilers. So then you compile it up and you get an executable, and that executable basically represents your design, and then you run it, and basically it runs just like your real design. And you also can, so if you're running let's say you're designing a chip, so you run it and you get this executable, and then this executable represents your chip. So if that chip, say, is a CPU, you run that executable, and it's sort of operating just like your CPU is. So if you set up the right framework, you can then feed it in a binary, and it'll actually emulate that code just like a real CPU will. A lot slower, of course, but and you run your CPU design. It also can be used like emulated. So if you don't make a true executable, if you like make a library, you can make a library that represents whatever design it is. So imagine you're making a plug-in card for a PC, for example. You can make a model of, say, a GPU or say a Tesla self-driving CPU chip or what have you. That plugs in through PCI, and you make a model of that, and then you can link that model in with the real kernel. So now the kernel thinks it's talking to real hardware, but it's not. It's talking to this model of hardware, and you now can develop your driver just like you would when you finally get your hardware back. So that helps you sort of save your time to market, because you can do all the software design ahead of time and find all the bugs where the software people thought you were doing something and the hardware people thought something else. And all the things that normally happen, we have multiple people disagreeing about what was supposed to happen, even though they thought they were all agreeing on what was supposed to happen.
It's a huge time saving. And sounds like a reasonably complex thing to design and develop as well. Verilator in itself, I mean. Yes. Well, it didn't start doing all these optimizations, and it started off as sort of a real simple, let's make it as close as possible to a language in equals language out. And then over time, you realize that, oh, well, if we just, made this little optimization, it would speed things up by 50% or what have you. And you keep going, oh, if this was multi-threaded, we'd get some really good performance gains. And then, of course, you do that. And you do get really good performance gains, but now it's, of course, that much more complicated. So you keep piling those things upon each other. And like any tool, there's some features that maybe aren't used that much anymore, but most of the code is doing the stuff that is used 95% of the time. So most of the code is valuable. Yeah. It certainly would be ominous to restart from scratch. So I'm glad it wouldn't happen. I'm not a big fan of throwing everything out and rewriting just because it feels. Yeah. Well, fortunately, the design decision relatively early on was to make things relatively partitioned. So like most compilers, it's got a bunch of stages. So once in a while, a stage is completely thrown out and rewritten, but fortunately, that doesn't usually result in much else around it having to change. So that was a good early design decision that paid off. Yeah. So someone who's familiar with sort of compiler design and development would feel quite at home looking at Verilator. Yeah, they'd feel quite at home. There's a few weirdisms, again, related to it being all this parallelism, so you don't have that in a normal compiler. But other than that, for the most part, people that are good at compiler design, come look at the website, come help us. Sorry, a little ad in there. Exactly. Sort of insert it. Yeah. They'd feel right at home, and they might find it entertaining to work on something that has sort of more hardware-ish parallel construct. Yeah, I'd think so. Adds a little challenge. Yeah, just a little bit. and it's interesting. Both being more hardware related and also massively parallel. I'm not sure my mind would be able to handle thinking. Well, I'm sure it would. Nowadays, if you want any good software performance, it has to be parallel, pretty much, right? And that usually doesn't work out on the first 4 attempts. So. No, that's true. Yeah. Concurrent programming is certainly a, maybe not quite a black art, but certainly on the realm of blackness art. It tends to land there somehow. You start off with a nice, clean conceptual model, and then you run into a strange problem. And then you just make it difficult for yourself somehow. Well, you realize everything isn't really reliable like it should be, and this goes down, or you lose a few packets and suddenly the world self-destructs. Yeah. Oops. Realize how uncertain everything is. So was performance always, was it a focus, or was it something that sort of evolved over time as something Verilator was? Performance was always a little bit of a focus. So when it first started, again, it was pretty simple translation, but it was still sort of faster than all the other alternatives we had. So we were pretty happy. Not that we would have liked it faster, but we were pretty happy. And
the bar sort of keeps moving. But still, for the most part, I should be careful of this. I'm sure there's something which outperforms it, but for the most part, on average, it sort of keeps the performance lead. The big boost was adding multi-threaded, so that obviously helped a ton. The next big boost will come from, right now it's basically limited by the CPU hardware, so it's limited by things like cache pressure and all these things that don't normally limit CPU performance, because it kind of took advantage already of all the other things that normally limit CPU performance. So now it's sort of hitting the microarchitectural problems of the CPUs. So we have some ideas for sort of how to push past that next wall. So we'll get hopefully another, couple factors of 2 at least. And then we need to figure out a bunch of whole new problems, which is, right now it still doesn't work that great scheduling between, like if you have a multi-socket CPU, it does really well on one socket, but the latencies, once you even have that extra 500 nanoseconds talking to another socket, it kind of falls apart. So that's sort of the next scale of problems. And then we have another scale after that we have a research proposal out for, which is try to actually schedule across multiple CPUs. So now you have, multi-microsecond latency. So how to do that on really large problems. So there's all these, all the way from the little end to building these super huge things where we can get some really good speed ups. But we need to, as with all things, we need people to work on it.
Yeah. You're pushing an envelope in an interesting way when there are research proposals involved for improving.
Yeah, exactly. Yeah.
So, and is all that on the website somewhere, like the performance challenges and what you're looking into and the proposals? Yeah,
there's we use GitHub, so we moved to GitHub about maybe 6 months, a year ago, which was a great thing, by the way. Certainly, before that, we had our own website that was getting a little dated and didn't really have the really good interaction tools that GitHub has. And there's other, of course, alternatives to GitHub, but in general, I would encourage open source. If you have a project that more than a few people are playing with, definitely move to one of the sort of community development tools. Anyways, a little aside there. So there's some GitHub issues that talk about some of these challenges and some ideas to get around them and some experiments to do and all that. And, another interesting thing is, so my real job is CPU design. So, and chip design in general. And, I kind of recognize that, there's a few little tweaks I'd really like to make them to the CPU architecture to make Verilator faster. But for the most part, I recognize I shouldn't use my influence inappropriately. So I haven't gotten there. I haven't gotten there yet. But, it is tempting. It would be nice to see some Verilated benchmarks as part of the spec-in suite, because this whole cache pressure thing is, there's a couple things which it pokes at CPU architecture that there really aren't any good benchmarks for. So it is a little tempting. But like all things, there's all sort of these fun things that would be to do as side project I haven't really had a chance to do.
Yeah. Do you know if there are any other popular applications that sort of hit the same bottlenecks without realizing it?
Things you've never heard of, like the Linux kernel. I'm sure you've never heard of that.
Yeah. Other people use it, I've heard.
Yeah. I mean, really big. A lot of the benchmarks that people use for CPU design, unfortunately, are much more either numerical or like GCC, which isn't really numerical, but it's, a data processing problem. But there aren't really, for good reasons, not that it's all bad reasons, but you can't really take the whole Linux kernel and say, let's make a benchmark out of the Linux kernel. It's not really a practical thing to do. It's just,
not quite.
It'd be pretty hard. Yeah, it'd just be too hard to package and understand and all that stuff. So, this is kind of one of those problems. I think we probably, in theory, if someone spent time on it, we could figure out how to make a good benchmark out of it. But no one's really done that yet.
No, there are other things to do as well.
There's enough other things to do, exactly. Someone's interested.
Yeah, exactly. Come look at the website. And of course, everything's linked in the show notes for the episode for anyone listening. So my aim is always that people should be able to look everything up that they're
exactly. Well, that's just kind of circle on our usual theme here. That's one of the things I like about open source is you get all the sort of natural linkages between products you wouldn't otherwise see if all you can see is sort of the outside of a product. You don't really know what the technology inside is, or if you want to understand how it does something, you really have no way of doing that.
Yeah. So what's the thing going on right now that you're most interested in, or most excited by, or most looking forward to getting done?
Well, those maybe slightly disjoint sets, but the things I'm most looking forward to getting done is there's a bunch of language expansion that's going on. So there's a verification subset called Universal Verification Methodology, I think it is, UVM. And that's what a lot of people use for verifying the chips. And that has a ton more sequential constructs because that's the way people like to write code. So it has things like classes and verification constructs like code coverage, and very complicated code coverage, and generation of sequences and assertions and things like that. So we're trying to basically knock off some of that language. So people can use Verilator more for a verification language as opposed to only a let's model the hardware kind of language. So I think that'll open a whole new subset of designs and verification people that'll be able to use it as a tool. And that's a multi-year thing. So that's part of the reason I'm looking forward to it being done, because I recognize it's a many-year project.
Yeah, makes sense. So yeah, you said those were kind of disjoint sets. So were there other stuff?
Yeah. I mean, I actually like working on the performance stuff, to be honest. I mean, that's sort of one of the more fun things to work on.
Yeah.
I especially like the low-hanging fruit, although there's not much left. Sometimes if someone points me to design and I see some simple little thing, it's like, oh wait, that could be much better, and you spend that 10 minutes and get a great boost. It's like, oh, you get sort of that adrenaline rush of well, it's never only 10 minutes, but maybe a day. But the days of that happening very often are pretty well gone. Once in a while it turns up, but so now it's sort of more of the look at a design and see how it's performing on a particular CPU. Like when the new AMD multi-die CPUs came out, that was an interesting thing to delve into. Is how do you partition for that? Which right now we're not doing a great job at, but it's an interesting sort of that feedback cycle we talked about. Someone changes the CPU architecture, so is there something you have to do to take best advantage of it?
Yeah, that must be one of those things you can start digging into and sort of disappear for months if you let yourself.
Yeah, exactly. Well, it's like these talks. It's you're talking about something, or you're looking at some code, and then you see something interesting, and you kind of go off on a tangent for a little while. And you're like, I probably should get back to what I was originally working on. Otherwise, it'll never get done.
Yeah. So do you have a sense of what the most common hardware that people run on? I mean, the ones that sort of makes most sense to optimize heavily for?
Well, it's definitely, it's definitely your typical x86 and Intel servers. Intel and AMD servers. So most of the people running this, they're running it on a server farm, or nowadays a cloud, which is effectively a server farm on steroids. Right. So that's definitely the common thing. People do run it on laptops and all that, but that's sort of the easier, so to speak. Like if you can run well on a huge multi-socket, multi-core, then you'll generally do pretty good on a 4-core laptop.
Oh yeah. So it's scaling
right.
down.
Right, scaling down usually works pretty good. Not always, but
no, just have to wait a little bit longer.
Right.
So we're almost out of time, I guess. Is there anything we should add to the end here? Any particular place people should go to find out more that we haven't mentioned already?
Well, certainly the website's veripool.org. So if you're interested in taking a look there, but in general, if you're interested in software design related to EDA, there's the CHIPS Alliance, and there's tons of other tools that we didn't talk about by other people that are working on interesting problems like synthesis, for example, and formal assertions is another sort of interesting area. Basically the idea that you have this design and you want to formally prove that, yes, this code really does implement an adder or something more complicated, and there's no way it can suddenly become a multiplier rather than an adder, and do the wrong thing and have your self-driving cars explode or something bad like that. So there's lots of other interesting projects if you're interested, because I definitely think the EDA open source community and also the hardware open source community is still very young, and it's definitely going to be a growth area over the next 5 years and beyond. Yeah,
I'm looking forward to lots of exciting stuff happening. Well, thank you so much, Wilson, for taking the time to come on the podcast.
Well, thank you for having me, and thanks everyone for listening, and obviously enjoy other podcasts.
Yeah.
Let me put it this way, Mr. Raymer. The 9000 series is the most reliable computer ever made. No 9,000 computer has ever made a mistake or distorted information. We are all, by any practical definition of the words, foolproof and incapable of error.